All right, thanks, Liz. So as Liz said, I'm going to be talking today about some of the work that I've been doing in an effort to create a sea surface temperature metric for E3SM. So I started working on this a while back with the goal of relating sea surface temperature to patterns over land in E3SM. So this could look something like examining the relationship of sea surface temperature variability to precipitation or chlorophyll patterns, for example. So an example scenario would be something like, how does the sea surface temperature variability in the northern Pacific, for example, affect precipitation availability over the Great Plains? So these are the kind of questions we're trying to answer. So to start to try to answer these questions, I began to look through the literature, and there's been quite a few recent studies that have examined sea surface temperature variability. So I'm showing a handful of them just as an example. But overall, they have basically the same conclusions. Sea surface temperature variability is mostly seasonal. When you deseason it, it's dominated by ENSO processes, along with other oscillations like the NOAA and the TDO. So I liked this particular paper because I thought it was really interesting. So one of the things they did was relate extreme precipitation events over land to El Nino. So this figure is showing that correlation for a number of different data sets. We have observations in the top left and a few of the models. So the gray dots in this figure are showing statistical significance. The green is a positive correlation with El Nino, and the orange is a negative. So you can see the results vary a bit, but overall, all of these are showing similar patterns. And I really like this approach. I thought it was really interesting. So this paper by Lee et al. Was similar, only it was looking at the relationship between the ocean, in this case, sea surface salinity in the Atlantic, and precipitation. So essentially what they found was that high salinity over the subtropical Atlantic corresponded with increased moisture, which converged over the southern U.S. So that's essentially what this figure is showing. It's showing the correlation between sea surface salinity in 4 different corners of the Atlantic. So those are the shaded areas in the figure, and the precipitation in different areas, specifically over the U.S., but it looks like they did it over other continents as well. So like the last figure, in this case, green is a positive correlation and orange is negative. So our goal is really to do something similar, specifically for the United States in E3SM using sea surface temperature. So to do this, we started by looking at the sea surface temperature and precipitation from a low-resolution pre-industrial run. And rather than looking at raw precipitation data, we used something called the Standardized Precipitation Index, or SPI. So this is a widely used index for characterizing drought. It can be used on a range of different timescales, which makes it really useful. So basically, you can use it on time series data of any frequency. And basically, you just calculate it by subtracting the precipitation from the mean and then dividing by the standard deviation, so it's really easy. So when you do that over the entire United States, you get something like this figure in the top right, which is a figure from NCAR. So in this figure, you have a positive SPI in the blue and purple colors. That indicates more moisture, and a negative one is the red color, and that indicates less or drought. So there's a range between red and the purple here, indicating if there's a drought or if there's a lot of moisture. So just as a side note, all of the analyses I'm going to show you in the next few slides look similar whether you use this SPI analysis or if you calculate a time series of extreme events. So it doesn't really matter which one you pick. So lastly, we wanted to look at the impacts on individual watersheds throughout the U.S. So we averaged all of our SPI data by the USGS HUC2 areas. So there's roughly around 20 of these. And this just helps us get a better idea of which areas may be more impacted across the U.S. And it's more of a natural delineation than using states, for example. Okay. So after you do all of those analyses and you plot them, they look something like this. So this is just showing the SPI over a typical year, so going from January to December. So in general, what you see is a strong seasonal cycle, so it's drier in the summer. So if you look at the August, it's very blue, so it's very dry. And there's more precipitation or more moisture in the winter. For example, if you look at February, it's very red and very wet. So while this is the overall pattern, there's still some variability among watersheds. So for example, if you look at the Great Plains in August, it's much darker, indicating that it's drier than other parts of the country. And if you look at it in May, you can see that it receives more moisture. So this just gives us a really easy way of looking to see what the drought patterns look like across the U.S. Okay, so this gives us a good look at the precipitation, but what about sea surface temperature? So one of the first things we did to look at sea surface temperature was plot the sea surface temperature anomaly when the precipitation in each of these watersheds, so these are the areas I've marked in red in the figure. And this isn't showing all of them, but it's just to kind of give you a general idea of what it looks like. So this is the sea surface temperature anomaly when in the watershed. The sea surface temperature anomaly when precipitation in the watershed is over the 95th percentile. So basically only when there's an extreme event. Then we stacked all of those on top of each other and averaged them. So the main thing that you can see here is that it largely looks the same regardless of watershed. So the anomaly off the coast of South America is associated with ENSO, and it's a pattern that tends to show up no matter which watershed you're looking at. So this is really useful. But if we want to look at these data as a time series or do any sort of time series correlations, we have to do some additional analyses. But overall, these figures do a pretty good job of giving us an idea of the types of patterns we're going to see. So to look at sea surface temperature as a time series, we need to remove the seasonal cycle from the data. Otherwise, we end up just correlating one seasonal cycle with another, and that gives us falsely high relationships as a result. So we did this with something called a Holtz-Winters decomposition. So this basically just breaks up the time series, which I've plotted here in green, into different components. So it breaks it into a seasonal component, which is the orange line, a trend component, which is blue, and the residual component, which is red. So when you add the red and the blue lines together, this will give you a better idea of sea surface temperature variability with the seasonal cycle removed. What we did then was we correlated the DC and sea surface temperature in the ocean with the SPI in each watershed over a time series of 50 years. And again, this is a low resolution DC and sea surface temperature. The shading is indicating the significance. So what this figure is showing is which sections of the ocean have the highest correlations with the standardized precipitation index in each watershed, and each watershed is again marked in red. So a positive correlation indicates that the sea surface temperature increases with SPI. So remember, a positive SPI is going to indicate more precipitation. So what this means is that warmer temperatures along the equator, where we see this ENSO-like pattern, is going to produce significant increases in precipitation across many of these watersheds. So it looks like there is a strong effect of ENSO that's happening here. And we also see similar patterns for the Pacific Decadal Oscillation. So we see areas of shaded significance in the North Pacific and in the North Atlantic as well, which means that the North Atlantic Oscillation is also playing a role. So we wanted to see what happens when we don't remove the seasonal cycle. So this slide and the next one are going to be showing March and September correlations. So this one is showing March, and it's basically the same figure as the previous one without the seasonal cycle removed. So it's showing March of all of the 50 years. And overall, you can see that it looks similar. But the biggest change, I'd say, is that the correlations look stronger, particularly in ENSO. We don't really quite see the same strong relationship in the North Atlantic and the North Pacific that we do, but overall, the same patterns seem to hold. And that's true of September as well. So we see a reduction in significance in this case, but overall, the patterns seem like they're the same. So what this is telling us is that these oscillations are driving the variability in precipitation in the different watersheds. So this figure is kind of just a different way of plotting that. So this is a quick comparison of deseasoned temperature in the rough location of where these oscillations occur with the SDI in each of these watersheds. And one quick note, this is the absolute value of the correlation, which is really just to give you an idea of whether or not there's an effect. So it's not telling it whether it's a positive or negative correlation. So it's just to kind of give you an idea of the geographical locations where it's playing a role. So what this tells us is that for the precipitatal oscillation and for ENSO, it primarily affects watersheds in the south and in the southwest. So the exact locations vary a little bit depending on which one we're looking at. While the North Atlantic oscillation is primarily affecting the Midwest and the South and the East as well a little bit. So none of this is really that surprising, and it's really a good ground truthing visual to make sure that we're on the right track. So the previous slide was just looking at the sea surface temperature variability at one point. So what we did next was took it a step further and calculated ENSO itself. So ENSO is calculated based on the NOAA Oceanic Nino Index, which is the surface temperature anomaly at Nino 3.4, which is in this box in the center. So when you calculate that time series, you end up with something that looks like this figure in the top right. So when you have a positive ENSO, that indicates a La Nina, and a negative ENSO indicates an El Nino. So what we can do then is look at the correlation between this time series and precipitation across the U.S. like we did before. So when we do that, we get this figure in the lower left. And this is showing a negative correlation in the north and a positive correlation in the south. So the interesting thing is that we can compare this data to NOAA, who have a similar figure, and their patterns overall look very similar. There's a slight spatial difference in exactly where the correlations are strongest, and the correlations are slightly stronger, which I think is due to the fact that we're averaging over much larger areas than they are, so that could be affecting it. But overall, the pattern seems to be more or less the same. And what this means is during an El Nino event, we should see more dry weather across the north and wetter weather across the south, which is typical of an El Nino. And this makes sense when you look at how an El Nino works. So you get the Pacific jet stream moving further south and dumping more water across the southern U.S., in contrast to a La Nina, which operates differently. So overall, this makes sense, and this is what we would expect to see in real life. So just like I just showed you with ENSO, we can do the same thing for the North Atlantic oscillation. So the NAO can be calculated as the normalized sea level pressure between Reykjavik and Lisbon. And this will give a time series like this one. So when we have a positive NAO, that indicates a strengthening of the Icelandic low and the Azores high. And a negative NAO is a weakening of both of those. So just like before, we can look at correlations between this time series and precipitation. And that gives us the figure in the lower right. So what we see here are stronger correlations in the southeast and along the east coast as well. And again, these results make sense when you look at how NAO works. So during a positive NAO, the jet stream and the storm track will be located further north. During the negative phase, it'll be located further south. When this happens, it could be dumping a lot more water over the southeastern U.S. So again, this is basically what we expect to see in this case. So just to summarize everything that I've talked about so far, we can now pinpoint specific locations in the U.S. where sea surface temperature affects drought or moisture in E3SM. So that's really exciting. So for example, in this figure that I showed before, we can see that variability due to ENSO is affecting precipitation in the lower Mississippi watershed, which is the one that's here in red. So following that, most watersheds across the U.S. are influenced primarily by variability in decadal oscillation, particularly ENSO and NAO. And lastly, NAO and ENSO affect precipitation patterns basically how we expect them to. So there isn't anything that we should be concerned about in terms of that. So we have a few different things in progress. So I was hoping to have these things finished to show you today, but the fact that Corey's been down for the past week meant that didn't happen, but we're planning on getting them finished up soon. So what I'm going to do is double check the high resolution output to make sure that we see the same pattern. Hopefully we do. And then take a look at the projection runs and see what happens to precipitation patterns and how that's coupled with ENSO and NAO and the PDO as well. So one thing that I think would be really interesting is to do the same analyses with chlorophyll instead of precipitation. So this figure is showing chlorophyll averaged across the U.S. for different seasons. So I think this could be another really interesting way of looking at the relationship of sea surface temperature on the U.S. And we'd love to hear any other ideas that you have as well. So we're in the process of writing this up into a paper, and we'll hopefully have this finished up soon. So that's all I have for you today, so I can take any questions.